So what was the trend that we looked at yesterday? ZEF. And what does ZEF stand for? Green sweatshirt.
Is it the effective nuclear charge?
Bingo, the effective nuclear charge. All righty. Continuing on with that, going across a period, so horizontally, what is the trend for effective nuclear charge?
Like if it's
Give you the direction and what it does in that direction.
okay. I'm going to the right, to the left, it increases.
Say that again.
Going to the left, to the right, it increases.
There we go. I thought you said it the other way around. The left to right, it increases. What about vertically? Up to down, top to bottom, it increases slightly. But yes, we're still going to say it increases. It's not as dramatic or drastic as it is going from left to right. Now, what we're going to talk about today, and we're actually going to cover probably just section 3 today. On Monday, I will be posting a video over section 4 that you need to watch, okay? Because we are having a quiz over the first 4 sections on Tuesday. That's the only way that I can get us to test over this chapter before spring break. So the Mondays that we're going to have over the next 2 weeks are going to be utilized for content. Okay? So just plan on that. Also, when you are watching the video on Mondays, okay, just like you are in class, make sure that you have your periodic table available. That way, when I provide you a trend, you can transfer that trend onto that periodic table. You can use that periodic table on the quiz. Okay? So make sure it is up to date. Anyway, in our discussion yesterday, I briefly mentioned about how the effective nuclear charge was going to play a role in what we're talking about today. So today we're talking about the size of an atom. Okay? And more importantly, what we measure in the size of atom oftentimes is called the bonding atomic radius. And so what that is that is defined as 1/2 of the distance between covalently bonded nuclei. So if we have 2 atoms that are bonded together, if we measure half the distance between the 2 nuclei of 2 bonded atoms, that would be the bonding atomic radius of a particular atom. And this is the extent at which 2 atoms can actually come together, because the nuclei are not able to get any closer due to that electron-to-electron repulsion. Now, this atom here, it's got electrons. This atom here has electrons. You try to bring them together and bond, yeah, you're going to be able to bond, but you're going to get some resistance from those electrons from both atoms. And they're going to say, all right, bub, you've come close enough. You're good there. You're not getting any closer. Okay? Now, each one of you was just given a piece of paper, or you grabbed a piece of paper as you walked in. Okay? It is this image that's on this slide. The reason why I gave it to you is simply because of this. We have some questions that are going to deal with these values. And it's a lot easier to see these values on this piece of paper than it is to see on your slide. So keep this handy. I'm going to be posting a PDF version of it later today at some point, just so you can have a digital version of it. But now you have a paper copy. Okay? So here is your second trend. All right? So we are talking about bonding atomic radius. As you go left to right, it is decreasing. So again, on your periodic table, if you look at my awesome periodic table that I'm drawing up here, as you go left to right, bonding atomic radius And you can do it however you want to. I like to keep it simple. So you want to transfer that onto your. You look confused.
I can't read it.
Oh yeah, I can see why. It says bonding atomic radius.
Which one do you want?
The one you did yesterday. So that one you're looking at.
So like on top of it?
You can on top, you can do it below it, anywhere you want to. It says bonding atomic radius decreases. Yeah, I kind of wrote that really badly, didn't I? So again, I'll say it again. Again. Bonding atomic radius decreases as we go left to right. And that is due to Zeph. Because as we go left to right, our effective nuclear charge is going to increase. And that increase in effective nuclear charge basically equals or equates to a stronger pull, a stronger attraction between the protons in the nucleus and the valence electrons. And so as effective nuclear charge increases, it's like a stress ball. It tends to squeeze it in tighter and tighter. So that's why the bonding radius decreases left to right. Now, as we go top to bottom, the bonding atomic radius increases. And that is because as we go from top down on the periodic table, we are adding energy levels. So we are actually getting further and further apart. We are getting larger as we go top down. So top down, and I'm just going to call this BAR just because that way it might be easier for you to see it, and I don't have very much room. So BAR increases. Again, that stands for bonding atomic radius. So left to right, bonding atomic radius decreases. From top down, bonding atomic radius increases. Now, as you'll see today, before we continue on, you will see today, there are some limitations when it comes to using the periodic table just as it is to make predictions. Okay, a lot of times there is a need for further information for us to make a judgment call. Again, as you'll see throughout this chapter, yes, there are some limitations to using just the periodic table. But for the most part, it's very useful in most situations. So what we're going to do, we're going to be utilizing this table that you picked up today to help answer these questions today. So the sample exercise up here says natural gas used in home heating and cooking is odorless. Because natural gas leaks pose a danger of explosion or suffocation, various smelly substances are added to the gas to allow detection of a leak. One such substance is methyl mercaptan, or possibly the odor that my daughter's soccer shoes smell like. But it has a formula of CH3SH. We are to use this diagram right here to predict the lengths of the carbon to sulfur bond, the carbon to hydrogen bond, and sulfur to hydrogen bonds in this particular molecule. All right. I want to shift your attention to this table you picked up. As you'll see on here, that each element listed on this table has a certain value. Those values are the bonding atomic radii for each element, the distance, okay? So, for instance, what is aluminum's bonding atomic radius? I know it's not one of the choices right now. What is aluminum's bonding atomic radius? 1.18. And another thing to add, since we are talking about measuring on the atomic scale, it has a label. And we've seen this label before, I think back maybe in chapter 3, possibly sooner. But the label, as you'll see at the very bottom, is in angstrom. It's the A with a little halo around it. So really for aluminum, it would be 1.18 angstrom. And so what we do to solve this type of question is simply add two numbers together. Raise your hand if you can do that. Higher! Higher! There we go. I can't see you. Faucet's in the way. So let's take a look. Carbon to sulfur. So find carbon on that piece of paper, and then find sulfur. Then add those two numbers together. Make sure you include the label angstrom, and that would be your bond length for that. So again, find carbon and find sulfur. What do we get? 1.79? Angstrom, yes. All right, next. Carbon to hydrogen. Yeah, I know they're listed up here. The answers are up here, but I still want you to find it. Carbon and hydrogen. What do we get? That's right. 1.14. Angstrom, yes. And lastly, sulfur to hydrogen. Sulfur and hydrogen. 1.39 angstrom. Very good. With me so far? Let's do a couple more. Practice exercise here. Using that same figure, predict which is longer. The bond in PBr3, so really what you're going to be looking at is phosphorus and bromine. Just have to do it once, phosphorus and bromine. And the acetine to chlorine. No, sorry, arsenic to chlorine. I was like, that's not right. AT is acetine. Arsenic to chlorine, my bad. In ASCl3. So again, first find phosphorus to bromine, and then arsenic to chlorine. Oop. Fire blanket, what'd you get? Well, actually, what'd you get for phosphorus to bromine? 2.2 angstrom. What'd you get for arsenic to chlorine? 2.18. So, who has the longer atomic bond radius? Or bond length, I should say? The two, what do you say? Oh. No. Oh. And that would be the phosphorus to bromine. The difference is that much, but it is in fact still larger. All right. So to revisit this trend, I've got this nice little reminder slide here. Again, within each group, the bonding radii tend to increase from top down. So vertically speaking, top down, we increase our bonding radius. Within each period, going left to right, we decrease our size. Now, we're going on to the next one. This time, we're not going to use any numbers. We're simply going to use location on the periodic table and our trends. So let's start off with a practice here. So referring to a periodic table, we are to arrange as much as possible the atoms of phosphorus, sulfur, arsenic, and selenium. Okay? In order of increasing size. Okay, and the only reason why the numbers on that sample question are given is so you can easily find them on the periodic table. But I'm going to tell you they're really close. So to answer this, we have to put the smallest first and end with the biggest. So we have to identify here. We locate phosphorus. Actually, I'm going to do this on the camera. So much stuff to move. Right there. So we identify and locate the elements. All right. I'm going to get a piece of paper so I don't run on here. So here's phosphorus. Here's sulfur. Here's arsenic. Here's selenium. So let's first take a look at phosphorus and sulfur. Which one of these two would you expect to be larger? Which one would you expect to be smaller? Using the trend. We're in the same period, and bonding radius decreases left to right. So which one would you expect to be smaller? Was that? Phosphorus? Sulfur. Because
Oh, you asked which one? No, not that.
that's all right. So sulfur, okay, is going to be smaller than phosphorus. Now, let's look at the other two right now. Arsenic and selenium. Who's going to be smaller? Selenium. Selenium will be smaller than arsenic. Okay. So, let's look at the two smallest ones, sulfur and selenium. Sulfur is just above selenium. So who would we expect to be the smaller of these two? Sulfur. It's above there, and the trend for this is top down. It gets bigger. So ultimately, that means that sulfur is going to be the smallest. Okay? Now, we're not certain where selenium is going to fall in the mix just yet. Okay? But now let's look at the two bigger ones. Okay? Phosphorus and arsenic. Phosphorus is above arsenic. So which one would we expect to be larger there? Arsenic, exactly. So, seeing that arsenic is the largest of the bigger ones, that means that arsenic should be the largest radii. Now, when it comes to phosphorus and selenium, we need to find homes for those. Okay, so let's go back to the question. So, yes, selenium. Okay, so our two periodic trends, as I'm reading here on your notes, for atomic size, do not supply enough information to allow us to determine whether or not phosphorus or selenium has a larger radius. Going from phosphorus to selenium in the periodic table, we move down, which we tend to increase, and to the right, which the radius trend tends to decrease. So, the only way to answer where selenium and phosphorus go requires us to access a secondary information source. This is one of those shortfalls that we come to. Okay, because phosphorus is to the left of selenium, which would make that according to the trend, even though it's not the same period, but those tend to be larger. But selenium is in a lower period. So where do we go from here? That's when we access our diagram from the last thing, okay, with the values. So if we find selenium, selenium is 1.16, and phosphorus is 1.06. So to finalize this, if you are required to do this, you're going to have phosphorus and selenium as your final answer. Okay? Let's do a practice one, because they're fun. All right. So we're down here at the practice exercise. Okay? We are to arrange sodium, beryllium, and magnesium in order of increasing atomic radius. Where did it go? Okay. So let's locate them. Sodium, magnesium, beryllium. Okay? So, all three are right here. Can anybody take a guess based off the trends as to who would be the smallest? Sodium, magnesium, or beryllium? Why beryllium? Perfect. It's a period above, and it's to the right as from some of the others, at least one other. So perfect. So beryllium's going to be the smallest. So that leaves us with sodium and magnesium. As you see, sodium and magnesium are in the same period. So using our trends, which one would be smaller? Did I say beryllium? Sodium, magnesium? I can't remember what I said. Sodium, magnesium. And you said what? Magnesium, yes. Magnesium is to the right of sodium. Therefore, according to the trend, it should be smaller. So we get magnesium and sodium. Yay. Didn't have to access that table for this one. Very good. Questions on that so far? No? Cool. Let's continue on. We got a little bit more to go in section 3. Okay. All right. We've got done talking about normal, regular, neutral atoms. Now, let's talk about ions. Okay. Ions, to refresh your memory, are atoms that have either gained or lost electrons. Okay? Cations, which are positively charged, are associated with metals and the loss of electrons. Anions are associated with nonmetals and are typically with atoms that have gained electrons. So when we are talking about ionic size, the fact of if somebody lost electrons or gained electrons is going to play the main role in determining what the size should be. So the ionic size depends on the nuclear charge, the number of electrons, and the orbitals in which the electrons reside. So one thing that we're going to notice here, and we need to really drill into our memory, is that cations are smaller than their parent ions. When we say parent atoms. When we say parent atoms, we just mean the neutral state, the neutral form of that. Okay? So, cations are smaller than parent atoms. If we look at lithium, this yellow atom here, that's the parent atom. That's the neutral form. The cation version, we lost an electron. we lost that outermost electron. So now what's happening is we have fewer electrons present in an atom of lithium. So the repulsion forces between all the electrons has been reduced. But also now we have an increase in protons, which are then going to even constrict it even further. So what do you think is going to happen with anions then? Again, if we're gaining electrons, what do you think is going to happen? Is the atom going to become smaller or larger? What do you think? Like going to a buffet. How do you feel after you go to a buffet? A little larger. At least I do. It just might be me. Anions are larger than their parent atom because now we are adding electrons, therefore increasing repulsions between electrons. So they want to go even further away. But also we are, this isn't necessarily mentioned, but now we have an abundance of electrons. And that pole of that once balanced pole between the protons and electrons is now imbalanced. Now more electrons are out there. The grip isn't necessarily as large. And so now we have a much larger anion than we do the parent ion. Next trend. This is ionic size. So, let me get my marker here. The ionic size. So as we go down a column, so top to bottom, ions increase. If you want to put ionic size, just to verify what you're talking about, ionic size increases. And again, just like before, the reason why the size of the ion going down increases is because of the value of N. We are increasing the number of energy levels. And then you might be wondering, what about horizontally? Okay, is there a trend horizontally across a period? And really there's not. Because initially, as you go from left to right across a period, and you're going through and you get to the end or towards the, maybe just past slightly the transition metals, you kind of leave the realm of metals. And so when you leave the realm of metals, you get into nonmetals. Nonmetals make anions, and as we just saw, anions are bigger. So horizontally speaking, there really isn't a defined trend for ionic size, just vertically. Okay? All right. So knowing this, we could take the idea of atomic radii, which we did in the previous sample, and ionic size to help answer these questions. So here we have Mg2+, Ca2+, and Ca, this time though in order of decreasing radius. So we know that cations are smaller than their parent atoms. So that means that Ca2+ will be smaller than calcium, Ca. Okay? And so looking at the periodic table, calcium is below magnesium. Okay? So just in regular atomic radius, which one would be larger, calcium or magnesium? Just normal, everyday, neutral atoms. Which one would be larger, calcium or magnesium? You can answer this question with atomic bonding radius, or bonding atomic radius. Which one would be larger? Calcium, exactly. Calcium is below magnesium. So, based on our earlier trend, calcium should be bigger. So, what that means is that between Ca2 plus and Mg2 plus, again, they're both the same ionic charge, okay? Ca2 plus is going to be larger than Mg2 plus, again, because it's below it on the periodic table. You probably can't see that over there, so I'm going to rewrite it over here. And Ca2 plus is going to be larger than Mg2 plus. And we already had mentioned that calcium, being the parent atom, is going to be larger than its ion of Ca2 plus. So, you want to ask yourself this question. Did I answer it in terms of what the question asked me to do? The question asked me to do them in order of decreasing radius. Did I do that? Yes, I did. I started with the largest one and ended on the smallest one. So we're probably going to do this practice exercise and then call it a day. Didn't quite get to section 4, but that's okay. That's okay. That is okay. So here, which one of the following atoms is the largest? I'm going to get another piece of paper. We've got S2 minus, S, and O2 minus. All right. So we're not asked to put these three in any order. It's supposed to determine who is the largest. Okay. So we're dealing with sulfur and oxygen and ions. All right, so here we have sulfur and oxygen right here on the periodic table. Let's zoom in a little more. Okay. Sulfur and oxygen. So between S2 minus and S, who would you expect to be bigger? Are we dealing with anions or cations right now? Anions. And so anions are what in terms of their parents? They are bigger. They're larger. So since this is the anion form of sulfur, which one of these would be larger? S2 minus, okay? So basically it takes sulfur out of the equation. But now we have to figure out, okay, well, I got O2 minus here. So now I need to look at S2 minus and O2 minus. O is above S. So which would we expect to be larger? S2 minus. Very good. And that would be your answer. All right, folks. Sorry to keep you to the bell, but I'll worry about the tables. I'll be creating a video with the remaining portions of 3 and into section 4.